prove this, we're going to make one simplifying assumption. We'll assume that the set of points is in general position. We will assume that no 4 points lie on the same circle and no 3 points lie on the same line. So we're going to use the empty circle property that we just went over it. So consider the 3 first vertices of a Delaunay triangulation. So we assume that I have a Delaunay triangulation, and this is the angle optimal triangulation. Look at the 3 vertices of one triangle. Let's say this triangle over here. We know that based on the illegal edge property, none of these edges are illegal, which means that this triangle, this circle must be empty, that it cannot contain any other input point. What does this mean? Let's look at the center of this circle, which is going to be this point over here. The main property of the center is that it is equal distance to all of the 3 points, because this is the center of the circle. So all of these 3 distances are exactly equal. On top of that, all of these red distances are smaller than all of the other distances from the center of the circle to any of the input point. This follows from the fact that the circle is empty. As a result, it follows that the nearest input point to the center of the circle are exactly these 3 input points. This is the definition of a Warner vertex, or was a property of a Warner vertex. As soon as I found one point that is equal distance to 3 points, and those 3 points are the closest neighbor of this point, then I know that that point is a Warner vertex. So, based on what we have proven, is that a triangle will identify one Warner vertex. Similarly, we could also use edges to identify Voronoi edges. Let's look at the center of the circle here. Based on what we just said, the distance from the center of the circle to these 2 points are equal, and these two points are the closest points to this center of the circle. Then it follows that there must be a Voronoi edge coming inside this center of the circle, and in fact this Voronoi edge is the bisector of the line segments that connect these 2 vertices. As a result, it follows that the face of that point, the face of this point, and the face of this point must be adjacent in the Voronoi diagram. Since they are adjacent in the Voronoi diagram, by the definition of graph duality, they will be connected in the dual graph. So this is pretty much the empty circle property is pretty much the only thing we need to prove the equivalence of the Delaunay triangulation and Voronoi diagrams. So I went over all these. As a result, since we know we can compute Voronoi diagrams in log n time, we could also compute the Delaunay triangulation in log n time, because computing the graph dual of a Voronoi diagram can be easily done in linear time.